Welcome back to PhysicsVault, the channel where we dive deep into the universe's biggest mysteries. No hype, just real physics explained like we're chatting over coffee. Today's episode is a marathon because this topic deserves it. Dark matter and dark energy. The invisible forces shaping galaxies and accelerating cosmic expansion. We're talking about stuff that makes up 95% of the entire universe, yet we can't see it, touch it, or directly detect it. Dark matter holds galaxies together like cosmic glue. Dark energy rips the universe apart faster and faster. Without them, nothing we see would exist. No Milky Way, no planets, no us. This is going to be a 2-hour journey. History, rock-solid evidence, wild candidates, the latest 2026 breakthroughs from JWST and DESI, the standard model, the tensions shaking cosmology right now, and what the future holds. Grab a notebook or hit pause when you need to. We're going slow and steady with analogies, animations, and simple math. By the end, you'll understand why these dark components are the biggest unsolved puzzle in physics. Let's start with the big picture. The universe isn't mostly stars and galaxies. Ordinary matter, everything made of atoms, is just 5%. Dark matter is about 27%, providing the gravity that binds everything. Dark energy is the remaining 68%, a repulsive force driving acceleration. How do we know? Decades of observations. But first, history. Let's rewind to the 1930s. In 1933, Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive group of galaxies 300 million light-years away. He applied the virial theorem, a basic physics rule relating kinetic and potential energy in bound systems, and calculated the cluster should be flying apart unless there was 400 times more mass than the visible stars and gas. He called it Dunkel Materia, dark matter. People thought he was off by a factor because Hubble's constant was wrong at the time, but the idea stuck. Fast forward to the 1970s, American astronomer Vera Rubin and her colleague Kent Ford used spectrographs on spiral galaxies like Andromeda. They measured rotation speeds of stars and gas. According to Newton and Kepler, speeds should drop off like 1/square root of radius far from the center. Visible mass only, but the curves stayed flat. Stars way out were orbiting just as fast as inner ones. That means extra invisible mass and a huge halo around every galaxy. Rubin's work in the 70s and 80s, plus radio mapping of hydrogen, convinced the field. By the late 70s, simulations by Ostraker, Peebles, and others showed galaxies need massive dark halos. Dark matter wasn't just a hunch anymore, it was required. Evidence today is overwhelming. 4 independent pillars that all point to the same invisible stuff. 1. Galaxy rotation curves, already covered. Flat everywhere we look, from tiny dwarfs to giants. Without dark matter halos, spirals would unwind. 2. Gravitational lensing. Einstein's general relativity says mass bends space-time and light. Massive clusters act like cosmic lenses, distorting background galaxies into arcs. Strong lensing, or subtle shears. Weak lensing. Measure the bending, map the total mass. Visible gas and stars account for only 10 to 20%. The rest, dark matter. Classic example, Hubble 1689 cluster. Lensing map shows a massive halo. 3. The Bullet Cluster, 2006, still the smoking gun. 2 galaxy clusters collided at 10 million mph. Hot gas, normal matter, slammed together, slowed by electromagnetic forces, and heated up, seen in X-rays. But gravitational lensing showed the mass kept going straight through, separated from the gas. Dark matter doesn't interact electromagnetically, it only feels gravity, so it passed right through like ghosts. Modified gravity theories struggle here. Bullet Cluster says non-baryonic dark matter exists. 4. Cosmic microwave background, CMB, plus large-scale structure. The CMB is the afterglow of the Big Bang, tiny temperature ripples from 380,000 years after creation. Planck satellite, 2013 and 2018, mapped these acoustic peaks perfectly only if cold dark matter existed early on. Without it, ordinary matter, baryons, couldn't clump fast enough after the universe cooled. Radiation pressure would blow structures apart. Dark matter, moving slowly, cold, created gravitational wells first. Baryons fell in later. Galaxies form in time. Simulations match the cosmic web we see today only with 27% dark matter. Extra evidence, galaxy cluster gas temperatures, dwarf galaxy counts, and even the 2026 JWST ultra-high-res dark matter map, twice as sharp as Hubble, showing the invisible scaffolding pulling normal matter into galaxies over billions of years. All lines agree, dark matter is real, cold, non-baryonic, and makes up 85% of all matter. So what is it? Not normal atoms. Big Bang nucleosynthesis limits baryons to 5%. Not black holes or dead stars in big numbers. Microlensing surveys like Ogle rule out most MACOs. Top candidates? WIMPs, weakly interacting massive particles. The classic favorite, particles of 100 times proton mass, interacting only via weak force and gravity. Produced in the early universe, their relic density matches exactly what we need if annihilation cross-section is right. Supersymmetry predicted them, but direct detection experiments, Xenon, Lux Zeppelin, Panda X, all null so far into 2026. LZ has entered the neutrino fog, so sensitive it sees solar neutrinos. No WIMPs in the expected range. LHC hasn't found super partners. WIMPs are fading. Axions. Ultralight bosons solving the strong CP problem in quantum chromodynamics. Mass around 10 to 5 eV. They're cold, produced via misalignment mechanism. Experiments like ADMX are tuning in. Renewed hope post-WIMP drought. Sterile neutrinos, right-handed neutrinos, warm dark matter. But too warm disrupts small galaxies. Ruled out as majority. Primordial black holes. Formed in the early universe. Some LIGO mergers hint at subsolar masses. JWST's little red dots over massive early black holes. Fuel speculation, but not the full story yet. Self-interacting dark matter or fuzzy dark matter, ultralight scalar fields, are niche models fitting some small-scale issues. Alternatives, modified Newtonian dynamics, MON. Tweak gravity at low accelerations to explain rotation curves without extra mass. It works amazingly for galaxies, but fails the bullet cluster, CMB peaks, and cluster lensing. Most physicists say, even if gravity is modified slightly, we still need some dark matter. Bottom line in 2026, no direct detection, but gravitational evidence is ironclad. We're hunting harder than ever. How the repulsive twin, dark energy. Einstein in 1917 added a cosmological constant, L, to general relativity to keep the universe static. Hubble proved expansion in 1929. Einstein called it his biggest blunder. In the 1980s-90s, cold dark matter models predicted too much clustering. Something was missing. 1998, game changer. 2 teams, High Z Supernova Search, Reese and Schmidt, and Supernova Cosmology Project, Perlmutter. They used type Ia supernovae, exploding white dwarfs with exactly the same peak brightness. Standard candles. Measure distance from brightness, redshift from spectrum, expansion history. Result, distant supernovae are dimmer than expected in a decelerating universe. The expansion is speeding up. Nobel Prize 2011 to all 3. Term dark energy, coined by Michael Turner. Multiple independent confirmations. Type Ia supernova. Hundreds now, including DES and Pantheon Plus catalogs. Farther ones recede faster. CMB, Planck shows flat universe. O to total, newer 1. Matter only, 30%. Need 70% dark energy to close the books. Baryon acoustic oscillations, BAO. Sound waves frozen from early universe plasma. Galaxies prefer certain separations. DSI and others measure these standard rules. Distances larger than expected without acceleration, large-scale structure, plus integrated Sachs-Wolf effect. Supervoids and superclusters imprint on CMB. Only works with accelerating expansion. All say the same. Acceleration started on 5 to 6 billion years ago when dark energy overtook matter. Properties: uniform, dilute. 1027, Keldium 3, only gravity, equation of state PR1, negative pressure. Density stays constant as universe expands. Main models, cosmological constant L, vacuum energy from quantum fields. Problem, theoretical prediction, 10T120 times too big, cosmological constant problem, but fits data beautifully. Quintessence, dynamic scalar field rolling down potential. Density can evolve. Tracker solutions solve. Why now? Coincidence. Phantom energy, W81, density grows, big rip, tears atoms apart in trillions of years. Modified gravity alternatives exist, but struggle with all data. 2026 bombshell, latest as of March. DESI DR2, second data release, plus dark energy survey, full 6-year analysis. Plus, CMB data show strong hints. Dark energy is evolving, not constant. W changes with time. Evidence at 3 to 4.2 sigma, depending on supernova dataset. Highest with DES year 5. Dark energy may have peaked 7 billion years ago and is now 10% weaker. Some analyses, Cornell Feb 2026, even suggest negative effective L. Universe could eventually slow and crunch instead of eternal expansion. JWST and upcoming Euclid Roman will test this hard. Lambda CDM still works, but cracks are showing. Put it together. LCDM, lambda plus cold dark matter, flat universe. Components, baryons, 5%, cold DM 27%, L 68%. Friedman equation governs expansion. OH to 2, orch refrac PA 3 home, yefrac KC2 A2, plus frac a lambda C noon 3 polar. We set K-sure 0, flat. Successes, predicts CMB power spectrum to 1% precision, BAO scales, light element abundances, structure growth, best model we have. But tensions in 2026, Hubble tension, local distance ladder, Cepheids plus supernovae gives H0 73 calendar S MPC. CMB plus early universe gives solders and 67s, tension 5s, evolving DE helps a bit. S8 tension, matter clustering amplitude, CMB predicts higher structure growth than weak lensing surveys, DES, kids measure. 2 to 3 ES, interacting DMDE models or slight growth suppression proposed. 2026, combined CMB, Planck plus ACT plus ESPT, and DSI data are tightening constraints but highlighting these cracks. New physics or systematics? Stay tuned. Euclid launch data and Vera Rubin Observatory will decide. Future experiments, Euclid, ESA. Plus Nancy Grace Roman, NASA, Wide Field Weak Lensing, and BAO for Million Galaxy Dark Matter Maps, DESI Full Survey, TWUS Vera C. Rubin Observatory, Billions of Galaxies, Direct DM Detectors, LZ Upgrades, ADMX, New Axion Haloscopes. JWST continues High Z Lensing and early black hole seeds. Mysteries remain. What particle is dark matter? Is dark energy constant or dynamic? Why 5 to 27 to 68 split? Coincidence or deeper law? Will the universe rip, crunch, or die in heat death? These invisible forces built the cosmos we live in. Understanding them is understanding our place in the universe. That's it for this deep dive. 2 hours of pure cosmology. Drop your questions below. Which part blew your mind? The bullet cluster, DESI's evolving DE hint, or the JWST map? Subscribe to PhysicsVault for more. Next episode, quantum gravity or black hole information paradox. Hit like, share, and see you in the comments. Stay curious. The universe is weirder than we think.